basically always have this fixed time interval, so we print every 8 hours. Next. And then it basically shows you the print time. You basically start first print time is 8 hours, 16:24. So you also could kind of enter this manually if you want to have like, if you don't want to have, for example, a constant time interval. Basically, you can specify this in this table. Push OK. Then it immediately goes to the next one. And this also is the same thing. You don't want to really mess with this unless you run into problems with convergence. So those are really only to maximize the iteration. Usually for simple problems, maximum number of iterations is 10. We can increase this a little bit to 50, but it's actually going to finish within these 10 iteration cycles. And then all those kind of iteration limits you want to keep unless you really run into troubles. And usually you get really into troubles, for example, when you have like layered systems and you have a very fine soil on top of a very coarse soil or vice versa. Then you have very big contrast in hydraulic properties, and in some cases then you need to start playing with those kind of iteration limits, or you need to increase the spatial discretization, especially close to this boundary, because maybe the spatial discretization is the cause, so it cannot really converge. Then, of course, for 1D problem, simulation time gets not really, doesn't cause any problems, but when you kind of work with rather complex 3D geometries, and you have like 1 or 2 or 3 million nodes, then actually it can take like, even with a very strong computer, like a few days to get one simulation done. But we can leave this. The only thing you can change is maximum number of iterations, but even if we leave it with 10, it shouldn't solve any problems. Then we go to next. Then here we need to kind of specify what kind of hydraulic model we want to use. And we go with the most basic one, Van Gogh model, so we talked about this last week. We have all those options. Because we have a uniform soil, we don't really need to deal with dual porosity. We also don't want to consider hysteresis for this. So it's only the Van Gogh model, then we go to next. And then we say we're going to model this for a long soil. And we basically use the parameters that are kind of implemented in Hydrus. So you have these textual classes, so there should be 12, coinciding with the USJ textual classes. So when we, for example, change from loam to sand, you immediately should see the residual water content, saturated water content, R-frame. So those are the Van Gogh parameters, hydraulic conductivity. This is the tortuosity coefficient, and we usually use this as 0.5. So if we put sand, you will see that those values are actually going to change. So now we have the implemented values for sand. We also said we could use like this Rosetta Light model from Marcel. So we can use neural network predictions. And here we actually can, if we have some information, for example, if I have the texture, if I know sand silt, clay content, or if I know the textural class, this actually doesn't make a lot of sense because the textural class is exactly what is already implemented in the soil catalog. But for example, if I would have particle size analysis and I would know sand silt and clay content, I specify this level, and it would need to enter sand silt and clay, and then based on this, it would, based on this field transfer functions, it would predict the Van Gogh parameters. Then if I have bulk density, I can kind of increase the certainty, so I can actually input sand, silt, clay, and bulk density. Then the values I get a little bit better founded, so they have higher certainty. Then of course you can go to the next step and you can implement the water content and field capacity. But those are usually measurements. If you have water content and field capacity, usually you already have most likely you measure the whole retention curve. So you can do this, and then you can basically add another step and can also enter the water content, the permanent wilting point. And of course, the more information you enter, the more certain your predictions or your Peter transfer predictions are going to get. But we don't really use this for now, so we cancel this. We said we're going to use the values for loam soil, for loam, and then it immediately finds those from the local parameter, etc. conductivity. But also the factor is actually always set at 0.5. So now we have the quality parameters for loam, and we go to next. Now we want to define the boundary conditions. So when you look at the instructions, you basically have a flux top boundary condition. We say that there is no flux, so we say constant flux. Bottom boundary condition, we actually have a constant pressure head boundary condition. And then we also say that we want to specify the initial conditions in terms of pressure heads. So constant flux. So when we go to the next one, we actually need to specify that constant flux is 0, so there is no influx into the system. Lower boundary is constant pressure head, so we kind of model pressure depending on the groundwater level. Implement this, and then the initial conditions we're going to specify in terms of pressure heads. And we go to next. And this is basically the constant upper boundary flux is 0. So we don't want any water in the system. And we say next. Then it asks you if you want to go to the profile application. This is like a visual interface that allows us to specify the initial conditions, that allows us to specify the spatial discretization, and we want to say yes. And then it says if we want to save everything before we go to the graphic editor, we say yes. And then this one opens up. There are quite a few things, so you can print this, you can save this, you can change the grid spacing, so those are the spacing between those plots. Then you can change the display option, I think the display colors if you want to. Then you have some kind of quick connect buttons for spatial discretization, material distribution. You can play for this, but you also can use those pull-down menus. So first of all, we want to deal with the profile discretization. So now we have basically starting with 0 at the surface, and when you actually move down,
Is it possible to display the values at different points? Like a scale of values on the side?
Actually, when you move over the
Since there's 100 nodes, does each node represent 2 centimeters as well?
This is like each increment is 2 centimeters, and then in between you have the nodes. And this actually, I think this is, so you actually see when you move over it with the mouse, you see the elevation in the bottom right corner. So if we want to leave this, so we basically, if we have 101 nodes, So one node is on the surface, one node is on the boundary. You have exactly 100 like increments. So we want to keep this. We of course could change this. So if you want to do, this is usually useful when you really, as I mentioned, when you have like layered systems and you have very high kind of deviation between hydraulic properties, especially the interlayer or the interface you want to increase the node density. When you change this, for example, to 201, you basically get 200 increments. You only see that the spatial discretization gets much more finer. I think you can go up to, I don't know how many, 1,000 or 9,000.
It's just going to prolong the amount of time it takes to calculate.
You know, those 1D simulations is always good,
Yeah.
especially for water flow. You know. But of course, when you do this in a 3D model, when you can talk to Mormon, he knows that this actually, even with a very high-powered computer, and 3D is actually also programmed for parallel computing. So you actually utilize all the physical and virtual cores on your computer for the kind of iterations. Even with a very high-powered computer, if you have a very complex system, simulation time is 1, 2, 3 days easily. But for this, you can add as many as you want. It's always going to go very fast. But I'll change this back because it's a little bit easier to see. Change this back to 101. This now is our spatial discretization. So the next thing is when we go to conditions, material distribution. This is what we already specified before. We say we have one uniform material from the soil surface to 2 meter depth. So this is basically one material, so it is plain where. So we don't need to change anything with this. Of course, if I specify 2, I can specify basically the layer thickness and everything, modify this also here. Then we go to, we don't do the scaling, we don't do the group distribution. Then we go to initial conditions. Fresh head water content. And we basically initially specified that we want to do this in terms of pressure head. So now when you look at your instructions, we say basically initially we want to, so initially we want to establish hydrostatic conditions with the pressure head at the bottom boundary at 0. Hydrostatic conditions means that there is no flow in the system. So when you think about gradient, what would we need to do so that there is no flow and that we have 0 pressure head at the bottom? So what does this mean? What pressure head I would need on the top? That there is no flow that hydrostatic condition.
Zero.
Think about it. We already talked about this. Hydraulic head is made up of pressure head. So pressure head is 0 and also of elevation head. So if I have a 2 meter deep profile, what does the pressure hydraulic head need to be on the top?
-2.
+2 or -2?
-2.
-2. You need to counterbalance this. So what we want to do now, we want to edit the conditions. So then you actually have a point, and then you only start with the first node and you go all the way down to the bottom one. Then you click. And then this allows us to specify the top values and specify the bottom values. And of course we need to uncheck this box because otherwise we always get design values. And now I know at the bottom I want to have 0 initially. And since I want to have hydrostatic conditions and my profile is 2 meter deep, I basically know that I need 200 centimeters pressure head, hydraulic head on the top. And I say, okay. Now I basically have this linear pressure distribution. It's linear distributed starting with -200, going all the way down to 0 to the bottom. Now I want to simulate a kind of spontaneously rising groundwater level. What do I need to do on the lower boundary condition? We say we want to make the water rise half a meter. To what value do we need to change this one? I need to change this from 0. So now I basically want to, so once this process is finished, I basically should have 0 at 1.5 centimeter depth. So I only go to edit condition again, and I only mark the lower boundary, and I plug in a value of, so once the water level is at 50 centimeter above the lower boundary, what's the pressure at the lower boundary? It's hydrostatic pressure. Now we have a saturated system. So I have I start with the soil surface, then I have 1.5 meter to the groundwater level, and then from the groundwater level to the bottom boundary it's 50 centimeters. So once this redistribution is done, what needs to be the pressure at the bottom boundary? It's exactly the hydrostatic pressure, it's 50 centimeters. So basically if I put 50 centimeters in here, I tweak the system a little bit. So now I have this initial distribution, it goes all the way down to a little bit above 0 at this node before the last node. And then I basically change this to 50 centimeter. What happens when I do the simulation? The water is actually going to rise into the profile. It's going to fill up the space all the way up to 50 centimeters. Is this clear, everybody? So we start out with hydrostatic conditions. Basically there is no flow. And then the groundwater table 2 meter depth. And if there is no flow, basically the pressure is 0. So we only need to take care of the elevation. Basically you get 0 potential at 2 meter depth. Elevation potential, which is basically the hydraulic cap, because small h is 0, this is minus 200 centimeters. So this is how I start off the soil profile, no flow. Then I want to make the groundwater table to rise from the lower boundary, where it is right now, 50 centimeters above the lower boundary. This happens basically if I change the pressure at the very lowest, at the lower boundary from 0 to 50 centimeters. Then basically water will flow into the system, the water level will rise, and it will stop exactly at 1.5 meter below the soil surface. This is basically rising water table, and then we do a second simulation with falling water table, where we actually have the water table established exactly in 1.5 meter depth. So if we have this case, what needs to be the again when we start out with hydrostatic conditions, what needs to be the pressure potential at the surface? If the water table is in 150 centimeter depth. Minus 150 centimeters. And then we do the opposite. So then we have like the positive pressure at the lower boundary, and then basically then we have this linear distribution, hydrostatic conditions, and then we set the lower boundary from 50 centimeters to 0 centimeter, which basically means that the water level declines until it reaches the bottom boundary. But let's do this first. So we say okay. So now we basically have a pressure distribution that goes from minus 200 to minus maybe, I don't know, 2 centimeters if those are actually 2 centimeter increments. And then only at the very last node, you basically have 50. When we start the simulation, it immediately leads the water, it immediately forces the water table to rise to exactly 1.5 meters below the surface, or 50 centimeters above because the hydrostatic pressure here is 50 centimeters. Then we close this. Save changes, you say yes. It only gives you a warning that whatever was in there first will be overwritten. Then it shows you this whole thing again. So we have the depth increments, we have the initial conditions. So now when you go down actually, so it's 0 with minus 200 centimeters. So when you go down all the way to the bottom, oops. So we go down like in the at 198 centimeters depth, we have minus 2 centimeters, and then we basically change the bottom one to 50 centimeters, which once we start the simulation makes water rise into the profile. If you see this, then there are scaling parameters we don't use, we don't kind of deal with root water uptake at this point. Material, so the material is the same all the way down for each of the nodes. There's only one layer, we don't have any, this is basically only the table representation of what we just saw in the graphical editor. And then we go to next. And then it basically tells us if we want to run Hydrus, we say okay. You will see this goes really, really fast. So you don't even, as soon as this terminal window opens, it's already done. And the only thing is you need to press enter. Now, basically, we have all our simulation results. And then there is a lot of output, visual output, so you can have profile information. So you can look at, so we have 8 print times, so we actually should see exactly 8 lines. We have 20, sorry, we have every 8 hours, so we have 21 print times, so you should see 21 kind of pressure distributions. We have depth, and then we have the pressure in centimeters, water content, solid conductivity. These are always like 21. So you actually can study the system based on those visual outputs. Hydraulic capacity, water flux, root water output we didn't simulate. Then you can look at, you can close this, you can look at boundary fluxes. And we are definitely mostly interested in the bottom boundary flux. So there should be like cumulative bottom flux. So since the water is flowing into the system, it's a positive flux. Outflow is actually upward flux is positive, outflux is negative. Basically, you see this cumulative flux. We also can look at the bottom flux. So this is basically the rate in centimeters per second. The other one is the cumulative flux. This is what we really are interested in when we want to calculate specific yield. We want to know how much water enters or how much water leaves the system. And since we are doing this for a 1D system, we don't need the volume of water. We basically get the length unit in centimeters. It's per unit area. So you have all this information. You have the solid hydraulic properties. So this is basically the soil water characteristic curve. Plotted a little bit different than we are used to. You can have the unsaturated hydraulic conductivity curve. So you also can actually change the, but in many cases you don't really see this with the scale. So So you can actually switch from auto scale. So go from 0 to 0.2.
How'd you get there?
Then we go axis. X-axis select. So you actually, sometimes you don't even see anything, but there are results there. You only need to change the kind of scale of the axis. So actually can change quite a little bit on this output. So there are, when you go through all this, I think you can change whatever kind of plot you want to have. This is actually relatively well developed. But in many cases it really makes kind of sense to actually take the data from the output files and do the analysis in Excel or another MATLAB or whatever other program you want to use. Runtime information is basically only tells you how fast this each of the time steps. Also simulations of over 168 hours. Then it basically tells you how fast each time step was, the iterations finished. There's not really any sense information. If you want to do mass balance between regions, you can find mass balance calculations. So, but now what we really want to do is send out this spreadsheet. I kind of played around with this a little bit so to make it a little bit easier to understand. So the first thing is now we basically kind of simulated water table rise, and we can get some information from those output files. And there is a node or kind of simulation node information file where we can actually get the initial moisture distribution. Then there is also a T-level kind of output file where we can basically get all the fluxes, boundary fluxes, and all kind of other parameters. It's basically the tabulated values that we see in those graphs. And the first thing is, so when you go to this folder, you basically, now we have this Hamburg 2 project. If you open this folder, this is where all those output files actually kind of stored. And initially we want to get the node information output file. So this is the first one we want to open, and we say we want to open this with, well, it's actually easier if you already have Excel open. So file open, go to browse, I have it on my desktop. See here, Homework 2. Then you need to change this to Word files so that you see the data files. And the first one we want to check is the node information out. We want to open. And this is actually this kind of structure so that this is in fixed width columns. So we have this one checked and then we go to finish. And now you basically have this node information file. For all the output times, and we want to get when you look at the instructions, we basically want to get the output data at 0 times, so this is basically the first one. And we basically, we have the depth increments, so go from 0, we don't need to do this, and we want to have the moisture distribution. So we want to copy this one. No, head moisture, this is the moisture distribution. Head distribution is what we specified initially, so this is what goes down into another last distribution. So we want to have the initial moisture distribution. So we enter this one, so copy. Then we go to our other spreadsheet. then we enter this one here, so we place the vessel of 1 to 3. And then elevation, when you go back to this other file, it starts with 0 and then it goes in 2 centimeter time increments all the way down to minus 200 centimeters. So now we got the same, so we start with 0, minus 2, minus 4, minus 6, and then this all the way down should end up with exactly minus 200 centimeters. They already set this up so that immediately plots you the moisture distribution. So in this graph, you basically see now we have it goes from low moisture content at the surface to the saturated moisture content at in the bottom. Then we want to calculate the equivalent depth immediately because we want to know the depth of water based on the moisture distribution that is stored in this profile. So we have 2 centimeter increments, and for those 2 centimeter increments,